This is 6.2.4.1. We are going to use the frequency domain approach to realize convolution. So basically, we have x of n, our signal coming into a LTI, linear time invariant system with impulse response h of n, and of course the output is described by the convolution of xn with the impulse response. In the frequency domain, we basically perform DTFT to get x of omega, and y of omega is simply the multiplication of x of omega and h of omega. This h of omega sometimes is written as this. So the omega here, that little omega, is the value here, where the capital omega here is representing our representation of the frequency domain, while ej omega is also the notation used in many books in our Z transform to represent the DTFT. So please don't be confused. This omega here is the value of this omega here later on when we substitute into the equation. Anyway, we know that y of omega equals to x of omega times h of omega, a much simpler computation in the frequency domain. Of course, once we get y omega, we need to get y of n by inverse discrete time Fourier transform. Now, please be aware, if we are going to use this equation to describe y of omega, then you must realize that y of omega is describing the output only in the steady state form. Okay, so if you ever need transient analysis, you cannot use the Fourier analysis. We'll show you the difference very soon, but let's proceed with this understanding. Okay, let's see how the output is described. Once we have x omega times h of omega, then this would be the magnitude, and of course the phase looks like this. Okay, and h of omega has a special name. It's called the frequency response. So every time when we say the frequency response of the system, we're talking about the DTFT of the impulse response. And simply it is the Fourier transform of Hn. That's the most direct form, but later on you will realize that we can use the Z transform to get h of z followed by h of omega later on. This has also a name. It's called magnitude response, and this angle of h omega is called the phase response. Please remember these names carefully, and then we'll use this often in the next few slides. Okay, in these slides I'm going to show you how we're going to calculate h of omega. The most direct way is to send the impulse here and to get yn. But although that's the most direct way, once you have gotten yn, of course, then you can then convert from h of n by DTFT. But we're not going to do that, because to do that, you have to simulate sending an impulse and getting the impulse response. Instead, we're going to get it via the Z transform. So this is how we're going to do. So I'm going to do the method 2. So I've told you that method 1 is simply DTFT of h of n. Method 2 is to via the Z transform. So what do? It is this step. We get h of z and we simply substitute z equals to ej omega. Okay, so how is this possible? This is possible only when the region of convergence of your h of z include the unit circle. So when that happens, means that the Fourier transform exists. Let's see the working now. So when we have y of n to convert to y of z, so y of n becomes y of z, x of n becomes x of z, and y of n minus 1 simply become 0.5, which is the coefficients here, 0.5 times y of z minus 1. So this is nothing but your good old Z transform. Okay, so once you have done that, then we can manipulate this algebraic equation, and then we'll bring y of z to the one side, and we bring this guy to the other side, and we have this y of z times 1 minus 0.5 z minus 1 equals to x of z. Now all we are going to do is to say that h of z, the transfer function, is defined as the output in the Z domain divided by the input of the Z domain. So it's y over z x of z. So you just bring x of z to that side, then you have living with times 1. So this 1, it comes from here, and this guy comes from this guy. Okay, and we don't like to deal with negative power of z, so we basically multiply by z on top. So we have z on top and z minus 0.5 at the bottom, and now we can sketch. So you can sketch this, and then we have a 0 here. This 0 comes from the numerator, and the pole is positive 0.5. So this is z equals to 0.5, and this is the real part of z, and this is the imaginary part of z, and this is 1, and this is minus 1, this is j, and this is minus j, and the ROC looks like this. So I'm now going to sketch in green. The ROC is external to this circle with radius 0.5 because the pole is sitting at 0.5 positive. Since the ROC touches the unit circle, therefore these values along the unit circle exist. So what is this value along the unit circle? You realize that when we substitute the values of the unit circle, what is the unit circle? It is nothing but a radius 1 with omega going from 0 to 2 pi, and this is it. So when we substitute z equals to 1 ej omega for omega equals to 0 to 2 pi, then we are saying these values here. And we can of course compute, so we just substitute z equals to 1 ej omega, and we get h of omega. And this is the DTFT of Hn, or actually we can call this as the frequency response of the system of Hz. Okay, so we now know how to get h of omega from this roundabout way of the z transform, but actually it only takes a few steps. If you have tried to find Hn and DTFT of Hn, then you'll realize that it's even more difficult, which is this step 1. So once we have h of omega, what do we do? Well, we know that our input has two types of input. The two inputs are 1, actually should be 1 un, means that it only exists for this, what they call that, from the right hand side of time, and un. But notice that actually you have 1 un, and if you try to perform discrete time Fourier transform of this, it won't exist. So here is, oh, I should not draw it this way, it should be infinity, and along here is n, and this is 0, 1, 2, and here. So if you try to perform the z transform of this, the Fourier transform of this, it wouldn't exist because it doesn't converge, it goes to infinity. But interestingly, if you throw away these uns and these uns, then you can take the discrete time Fourier transform of constant 1. You can take the discrete time Fourier transform of constant 0.1 pi n without the un. It exists. Okay, so it's a little bit tricky at this point, but let's proceed. So we have two signals, one of them is 1 and the other guy is this. So we are not thinking about that step anymore at time n equals to 0. Now, what is the frequency of this signal? The frequency of this signal is of course omega equals to 0.1 pi. What about this? The frequency is omega equals to 0 radian per second, or radian per sample. At every sample, we are not changing its value, so it's always 1 throughout. So we now need to see the frequency response at omega equals to 0 and omega equals to 0.1 pi. So this is it. We go ahead and substitute these two frequencies to get h of omega at these two frequencies. So omega equals to 0, simply we are substituting ej omega divided by ej omega minus 0.5, we're simply substituting what this omega equals to. So this guy is, when omega equals to 0, is 1 divided by 1 minus 0.5 equals to 1 over 0.5 equals to 2. That's it. And then of course you can substitute 0.1 pi into same ej omega and ej omega minus 0.5. So you substitute the 0.1 pi here and 0.1 pi here, and then you have this. So please use a calculator that can do complex number division so that you get this. Okay, so we will get the magnitude and the phase response at this frequency. That's the idea. Now, so how do we calculate the output? This is the real trick. In the frequency omega equals to 0, our original input is 1. The frequency response tells us that he will change the magnitude by 2. So 1 becomes 2. So in fact, this is the original 1 times the gain 2. What about this guy? 1 cosine 0.1 pi n. So the original input is 1 times the magnitude. What is the magnitude response? 1.829 from here. Alright, this little guy here. And therefore, and this 1.829. So 1 times 1.829, that's why it comes out as this value here. Now, then the original signal has 0.1 pi n. So remember, cosines are eigenfunction. Cosine of this frequency goes in, the same cosine comes out, the same frequency. The magnitude is now changed by this frequency response, as well as the phase. So this minus 2.865 comes from here, this value here. So this minus 0.2865 means at this frequency of 0.1 pi, the sinusoid will be delayed by minus 0.2865 radian. Okay, so this is the general idea. So now I write for you all these important numbers. So this is the gain. 2 is the gain at omega equals to 0. 1.829 is a gain at this guy. So notice that our input was 1 and 1. That's why, I'm just telling you this again. But honestly, if I give you other values, then you must be multiplying with the original other values. Anyway, so this is the steady state response of yn. Okay, now there's a very small thing that you should note. Now remember, I'm sending you not yun anymore, or 1 cosine 0.1 pi un. That's why these 2 last forever. And this 1.829 doesn't last from n equals to 0 to infinity. It lasts forever from negative time index as well. But this is what we're saying. This is a steady state response of the system. So we are now done with the steady state response by Fourier analysis. And if we want to now compare how we do it in MATLAB, so this is the next slide. In MATLAB, we'll take the Z transform and we'll get the coefficients, and we substitute the coefficients of B and A. So this is the coefficients of B, this is the coefficient of A. This is how we get it. Okay, how we find the coefficients? Simply we write the difference equation, take the Z transform, representing as H of Z equals to this, and we now collect the coefficients. The coefficients on top is B, and the coefficients in the bottom is A. Okay, in this descending order of Z. Once we have B and A, we use this MATLAB called FV2 and plugging in the B's and the A's coefficients, and it will out pops all these little diagrams for us. You can plot the pole and 0. So this was what we have in the previous diagram as well. The pole is at 0.5, 10 at the origin. We can also plot the impulse response H of n. Voila, and this is the impulse response that we can actually take the Fourier transform, but it goes to infinity. Anyway, the magnitude and the phase response is what we are after, because this is H of omega. And where is this omega? This omega is along here. This guy is omega from 0 to pi. So this, you see, is reference back to pi. From 0 to pi, I draw 2 lines for you. One is a blue line and one is a red line. So I'm interested in the frequency 0 0.1 pi because that is our cosine. So at 0.1 pi, I read these two numbers. The magnitude is 1.826 and the phase is minus 0.28, which is exactly what we have calculated. Then of course we have this, which is, and this, so magnitude is 2 at frequency 0 and the phase is 0. So this axis here on here is for the phase, and this axis here is for the magnitude, which is the blue line. BLUE is the magnitude and the red one is the phase. So what I've done now is I've gone through how to use FV tools, and then for you to check your results against your working using the previous approach of Fourier analysis. That's it. Thank you.